Welcome. Today, we're going to dive into a story of applied engineering. That is, and I'm not exaggerating here, like a modern-day moon landing. But it's all happening on a scale so small, you literally can't even see it. It's a story about reinventing the very building blocks of our digital world, all to push right past the known limits of physics.
For decades, it was simple. There was one number that told you everything you needed to know about progress in computing, the nanometer. Smaller was always better, period. But then, that simple, powerful story, it just started to fall apart, creating a real crisis for the entire industry. Okay, let's trace this journey for a second. Back in '95, if a chip was called 350 nanometers, that was a real physical measurement you could find on it. But pretty soon, the name started to drift away from reality. It became more of a label for a generational leap. Fast forward to today, and when you see a 3-nanometer chip, there is literally no single part of that transistor that actually measures 3 nanometers. It's basically just a brand name now.
And that's where things got really messy. A 7-nanometer chip from one company wasn't the same as a 7-nanometer chip from another. And this was a huge headache for Intel, because their 10-nanometer chips were actually denser than their competitors' 7-nanometer ones. But just because of the number, the market saw them as being a whole generation behind. A massive perception problem.
So, facing this wall, both technologically and in marketing, Intel did something incredibly audacious back in 2021. They didn't just announce a new roadmap. No, they announced a mission to launch an entirely new era for computing. And they started by completely changing the language of the game. They declared the dawn of the Angstrom Era. I mean, the name itself is just a masterstroke. Angstrom resonates with the atomic scale, right? It signals a change so fundamental, so profound, that the old language of nanometers just wasn't going to cut it anymore. This was their one small step moment.
So what in the world is an angstrom? Well, it's simply a smaller unit of measurement, 1/10 of a nanometer. But choosing it was a brilliant move, both psychologically and practically. It gets rid of those awkward decimals like 1.8 nm and gives you a nice clean 18A. It creates a whole new runway for progress, signaling that, hey, we are now operating at the scale of individual atoms.
But you can't just declare a new era and call it a day. To make this real, they had to do more than just change the name. They had to reinvent the most fundamental component in all of computing, the very engine of our digital world, the transistor itself.
For over a decade, the workhorse, the undisputed champ, was the FinFET transistor. Picture a tiny, vertical fin made of silicon. The gate, which is like a light switch, wraps around that fin on 3 sides to control the flow of electricity. It was a revolutionary design, and it powered an incredible amount of progress.
But as engineers tried to shrink it even further, the FinFET hit a hard physical wall. I mean, the fins just got too thin to work properly. And that 3-sided gate, it just wasn't enough to stop precious electricity from leaking out when the switch was supposed to be off. Moore's law was grinding to a halt.
The solution is this revolutionary new architecture called gate-all-around, or as Intel calls it, RibbonFET. So instead of wrapping the channel on 3 sides, the gate now completely surrounds it on all 4 sides. Think of it like a hand gripping a rope from every direction. Total control.
Now let's just put these side by side, because the difference is night and day. RibbonFET's 360-degree control practically eliminates that power leakage. But here's the real game changer. It gives designers the ability to perfectly fine-tune performance just by changing the width of the silicon ribbons. That's a level of flexibility they've never, ever had before.
Okay, so you've built a revolutionary new engine. Fantastic. But you still have to get fuel to it. And for decades, the plumbing inside a chip has been creating this massive, performance-choking traffic jam.
Just think about it for a second. You've got billions of transistors that all need 2 things: power to run and signals to tell them what to do. And for forever, the wires for both were crammed together on the front side of the chip, all competing for space. It was a complete bottleneck.
This bottleneck leads to a problem called voltage droop, which honestly is just a fancy way of saying you've got weak fuel pressure. The power that actually reaches the transistor is lower than it should be, and that puts a hard cap on the chip's top speed and wastes a ton of energy.
So what was Intel's solution? Well, it was radical, it was elegant, and it frankly sounds like something out of science fiction. After they built all the transistors on the front of the silicon wafer, they literally flipped the whole thing over. This is an industry-first technology. They call it PowerVia. And what it does is create a dedicated superhighway for power on that newly exposed back of the chip. This completely separates the power wiring from the signal wiring on the front. No more traffic jams. It's brilliant.
And the impact of this is just staggering. Just by separating the wiring, not by changing the transistor, just by redoing the plumbing, Intel showed a boost of over 5% in clock frequency. A 5% performance jump from plumbing? That's absolutely incredible.
So, by pulling off this moon landing of two massive breakthrough technologies at the exact same time, RibbonFET and PowerVia, Intel basically fired the starting gun on a new, incredibly high-stakes race between the world's top 3 chipmakers.
And this chart really lays out the different strategies. You've got Intel going for this high-risk shock and awe approach with its 18A node, throwing both breakthroughs in at once to try and leapfrog everybody. Then you have the market leader, TSMC, being much more cautious, splitting these innovations into 2 separate steps to de-risk the whole transition.
And here's the crucial point. The old Moore's Law, the one that was all about shrinking transistors to cut costs, that's over. We're in a new era, Moore's Law 2.0, you could call it. Now progress comes from this complex mix of breakthroughs in the transistor, in power delivery, and in advanced packaging, all working together in harmony.
But all this progress, it comes with a jaw-dropping price tag. The cost of a single one of these silicon wafers, the raw pizza dough for chips basically, is rocketing past $30,000. And that fundamentally changes who can even afford to play at the cutting edge anymore.
So why does any of this tech jargon matter to you? Well, it means the future of computing is going to be way more specialized. The most powerful, most expensive chips will be reserved for high-end stuff like AI and super premium devices. Meanwhile, all the older, cheaper nanometer nodes are going to keep powering the majority of our electronics for years to come.
Which leaves us with the big question, the one that's going to define the next decade of tech. Intel's high-risk, high-reward moonshot, could it let them jump an entire generation ahead? Or will their rival's safer, more measured path prove to be the smarter, more sustainable strategy in the long run?
We don't know the answer yet, but either way, the winner of this Angstrom Era arms race is going to define the future of everything, from our phones to our cars to the AI that powers our world. The race to the atomic scale has only just begun.